Hey there.
How now, brown bureaucrats?
Okay, brown cows. So we've got real quadratic equations. We're going to look at things we already know and things that we've recently learned, and this will put us moving in a slightly more broadened direction in terms of quadratic equations. So you can see there we're looking at a form where we have our good old friend ax squared plus bx plus c, where a, b and c are real numbers. Those coefficients there are real, and below that we can see our beast, the quadratic formula using the same a, b and c. We can see that that will help us find solutions. The delta, or the triangle, meaning discriminant, and it's a way of working out on the spot how many solutions and what type of solutions they are. We can see that if we have a positive value of the discriminant, that's what the triangle means, the discriminant, it means that there are, well, we say there are two real roots, okay? And if the discriminant is equal to 0, however, to say that because the discriminant is equal to 0, it does not mean actually that there are no solutions or no real solutions. There's more to it than that. And they haven't been telling you the whole truth. So here it is.
You can't handle the truth!
Okay, so previously no real roots if the discriminant was less than 0. In other words, if b squared minus 4ac is less than 0, or a negative, in other words, we would say that, yep, there's no solutions, just forget about it. But that's not the truth. We have two complex conjugates of each other, okay? So there are actually two roots. There are two roots, and they are complex in nature. So that's why before we studied complex numbers, we would say there's basically no roots, or no real roots anyway. So if we have a negative discriminant, two complex roots which are conjugates of each other, and we have two real roots if the discriminant is positive. As we've always said, if the discriminant equals zeros, we have two real double roots, so we have the plus or minus going on, so they're double roots. So we always have two roots, always. Here's a quick example here where we're going to use a quadratic formula, determine the roots, x squared minus 2x plus 5 equals 0, and we've got our substitution in here for the first line of our quadratic formula. You've used it before. It's all business as usual until we get down to the square root of negative 16. What we can do there is call that negative 1 times positive 16. We can use our laws of surds to split them up, because we want to see a square root of negative 1, and we can see that if we take the square root of 16 we get the 4, and we can also see that the square root of negative 1 there is I, so we have 4i. We can take a factor of 2 out of those three terms there, and the denominator becomes 1, so we don't actually see it there. 1 plus or minus 2i, so conjugates 1 plus 2i, 1 minus 2i. So we have complex roots, okay, and they're complex conjugates of each other. It's CTS time. CTS time, completing the square. We can look at the same quadratic and we can complete the square. It's a real quadratic, and I'm not going to go through all the details about completing the square, because watch one of my other videos, but basically this part here will be a completed square, and we have to add 4 on to retain the 5 from the previous line. We can see there in the factorized form we have x minus 1 all squared. We have the 4 there. Now with the 4 we can write minus 4i squared. We'll retain the plus 4. because I squared is -1, we have -4 times a -1 times a 4, which is +4. I'm sure you'll agree. And we can also see that we sub that in there in green, and all the while it equals 0 because we are solving. Now we've gone from SOTs, sum of two squares, see, that's 1 and that's 2, to dots, difference of two squares. And dots is good because we have two parts of an identity that follow on after that. A squared minus b squared is a plus b, a minus b in factorized form. So we've got x minus 1 all squared minus 4i squared, and we can then put that in the aforementioned form, the a plus b, a minus b. So if x minus 1 all squared is a squared, a would just be equivalent to x minus 1, and minus 4i squared will just become plus 2i, because if 4i squared is the square, the original was 2i. And we can see that we have a conjugate there because we have to follow our difference of two squares pattern there. One's a plus, one's a minus. Sub them in, remove the internal brackets, and then NFL, it's not a brand of football, we are at the null factor law stage. Okay, so we have the first part of the null factor law, x minus 1 plus 2i. Yep, and remember that's got to be solved so that we end up with an x equals, all right, which we're used to, x equals something. Well, x equals, add 1, take 2i, x equals 1 minus 2i. And the other one, the conjugate, we do the same thing, so if we've got to add 1 and add 2i, so we get the same answers as we got above. So that is a quick couple of examples and a quick tour through the new and the old to do with the real quadratic equations.